Swayam Prabha. Digital India. Educated India.
Welcome back to the class. Today we are starting a new topic on monitoring around landfills. Since landfills are repositories of waste, we are always bothered whether they are polluting the environment adjacent to it. We may design a very well-engineered landfill, we may put a cover, we may put a liner, but still we are bothered about, is it causing dust pollution? Is it releasing methane to the atmosphere? Is it causing bad odor? Is it contaminating the groundwater? Is it contaminating the surface water? So we need to monitor landfills. And let's understand that monitoring a landfill above the ground or on the ground surface is similar to monitoring any industry, right? So in an industry you do air pollution monitoring and you do water pollution monitoring. So how do I do water pollution monitoring in an industry? I have water which goes into the industry and I have water or wastewater which comes out of the industry. So our environmental monitoring always means checking whether the water which is coming out from the industry is polluted or not. And against what standard do we check that? Is it worse than the water which went into the industry, or is it better than the water which went into the industry, or is it the same? So ideally, whatever is the water which we supply to an industry, whether it is used as a cooling water, whether it is used as a process water, when it comes out of the plant and goes back into the drain, it must be as good as what it went into the industry. Okay? So that's the way we monitor liquids. Similarly, we monitor the air around the industry. If we are bothered about dust pollution, if we are bothered about SOx and NOx coming out of the chimneys, then we have to monitor the emissions. Now typically it's easy to monitor water because it comes out in a pipe or in a drain. It's more difficult to monitor air pollution because some of it will be coming out of a chimney, so you can monitor it where the emissions come out. But construction site, dust pollution, where are you going to monitor it? It's not coming out of a chimney. Then you have to do large area monitoring, or you have to monitor at the perimeter. In a landfill, I am going to not talk that much about the air pollution, and I am not going to talk that much about the water pollution because these are standard practices. You will treat a landfill just like a factory or an industrial plant, and you will use the same techniques that you use in industrial plants for environmental monitoring. What is important about a landfill is the subsurface monitoring, which is not routinely monitored everywhere. We may cursorily monitor it, but we don't routinely monitor it. So let's look at subsurface monitoring around landfills. First we'll develop the overall view, and then we will look at the specifics. So what do we monitor? As I said, we monitor air contamination, we monitor surface water contamination in landfills, and we also monitor subsurface contamination. When you do air contamination, you are only dealing with the gaseous phase. And when you do surface water contamination, you are dealing with liquid phase. When you do subsurface contamination, you are dealing with all the three phases: the solids in the soil, the liquids in terms of groundwater, and if you have the unsaturated zone, then in the pore space you will have some moisture or you will have some pore gas. So you're doing 3-phase monitoring for subsurface contamination. It's simpler to monitor the saturated zone because you can extract the groundwater and monitor it easily. And before you undertake any monitoring, you need to understand what are the contaminants of concern. Which is the contaminant you want to monitor? You can't say, I'll monitor this landfill without having pre-specified what is your contaminant of concern. So in a landfill, for example, in air, though we are not going to talk about it, what would be your contaminants of concerns? In air, you'd be bothered about methane emissions, you'd be bothered about volatile organic compounds, you'll be bothered about smell, you'll be bothered about dust, you'll be bothered about smoke. So you have different contaminants of concern in the air. So if you are going to monitor all these, then you have to put up the sensors or the samplers which can address these contaminants of concern, right? So a suspended solid or a dust monitor is not going to be the same as a methane monitor. So you'll have different samplers and different techniques for monitoring different contaminants of concern. Where do you monitor? Where means at what locations? Well, if I have a industrial plant, I would like to monitor, let me just take an example. That's my urban environment. This is an industrial area. This is residential. And within that industrial area, you may have a particular industrial plant within a boundary. Right? So I want to monitor I will have to monitor the environment. So it's we should monitor above the ground. So I would like to monitor here. Am I sending out something into the atmosphere? I should monitor around the ground surface. Am I allowing something to flow out on the ground surface? And when I'm talking of that, I'm talking of drains and discharge points. In the landfill, I will also monitor on the landfill cover. Here there's no landfill cover. There's no landfill cover here. But in a landfill, I will have to monitor the landfill cover also. And then I want to monitor below. I want to monitor below the ground surface. And finally, what is the contaminant of concern? Unless I monitor inside, unless I know what are the processes which are taking place inside, I'm not going to be able to identify the contaminant of concern. So maybe I'll monitor here, I'll also monitor here, I'll monitor here, here. So within the thing. So if I look at what is listed here, for a landfill, monitor above the ground, monitor on the ground surface, in the drains, you have stormwater drains, you have pipe drains at discharge points. You monitor on the landfill surface, where the cover is there on top of the cover. You monitor below the ground in the vadose zone, that is the unsaturated zone, and in the saturated zone, and you monitor within the waste. And how do you monitor? How do you monitor what you want to monitor? Well, I can take a sample and take it to the lab. But some of us would want real-time online monitoring. So maybe I'll have a sensor which you place there and it will start giving you readings. Please understand, the accuracies may not be that high. For example, if you want to monitor a particular contaminant of concern, if you take a sample to the laboratory, you will target determining that contaminant of concern. Suppose it is total dissolved solids, then you will evaporate the liquids and determine the total dissolved solids. But when you say, no, I want an online monitor which can tell me instantaneously what is online reading of the total dissolved solids. Well, you can have a sensor, but it may be an indirect monitor. Instead of measuring the total dissolved salts, it will measure some electrical conductivity and then it will use some correlations. So online may be fast, but may not be that accurate. So you can do sampling and lab testing, you can do in situ testing or in situ indirect monitoring, and normally direct and sampling is the most accurate, and indirect and in situ requires recalibration time and again. So those are the philosophies that you can have for monitoring. How often would you like to monitor? Every second, every hour, every day, every week, every month, every year, every 10 years? Any ideas? How often would you like to monitor? So it's being said, if it is hazardous, we will monitor more. Any other thought? How often you should monitor? We should monitor after the end of every season, and presuming that we have a season which changes every 3 months, he is saying he would like to monitor every 3 months. If I am monitoring dust from a site, then a once in 3 months doesn't make sense. And dust may not be that hazardous like arsenic, but would I monitor dust more often, or would I monitor arsenic emissions more often? So the issue is, I am trying to monitor something. If it doesn't change very rapidly, I don't have to monitor it very often. If it changes gradually. But if it changes very rapidly, then I have to monitor more often. The idea is I should be able to capture the peak. I should not be losing the critical concentration. Is that right? Basically, I want to know. So it's very easy not to be able to catch the critical contamination. Very easy. In fact, it's very difficult to say, all right, I have got the most critical reading of the contamination. So I can do it, as I said, I could do it hourly, I could do it daily, I could do it weekly, I could do it monthly, I could do it annually or biannually, and I could do it after extreme events. And the important thing for you to remember is, if it is changing very fast, then I have to monitor more often. If the dust emissions are going to be high during high wind, or if they are going to be high during a particular event or an activity taking place at a construction site, I should have my readings going on. But at what speed does groundwater travel through the ground? The rate of movement of water and the rate of movement of air is much higher than the rate of movement of groundwater. I told you a groundwater may travel a feet in 1 year in low permeability soils and several hundred feet in a year in a high permeability soil. But in the same 1 year, water may have traveled from the Himalayas to the Bay of Bengal because it travels much faster. So if you are doing something below the ground, it doesn't have to be done every second. It doesn't have to be done every hour. Even if you do it once a week or once a month, you may still not lose the critical event. But if you are looking at stack emissions, well, I would like stack emissions or chimney emissions to be monitored continuously. Why? Maybe the whole day the chimney doesn't throw out anything. While you are sleeping, it starts bellowing out a lot of smoke and a lot of other substances. So it all depends on how often it can change. What are the locations? We already said above, we said below, but if you look at the locations, you have to identify the locations in plan. I didn't even show the plan of this factory, but I have to look at it in section. But the ideal answer is, I would like to monitor everywhere. I'm not going to let you get away with it. I want to monitor everywhere. Is that possible? Seems utopian. So maybe I will monitor along grid points. Maybe I'll monitor along lines, the perimeter. My concern is that the industrial plant or the landfill should not be impacting the people outside the industrial plant or the perimeter. So maybe I'll want to do it on the perimeter, along grid points. I definitely want to monitor at inflow, and I definitely want to monitor at outflow. So I must know the quality of air which is coming in. So there will be a wind direction. The wind direction may change. You need the windrows diagram. But you must have, for the purpose of saying that something is being contaminated, you must have the inflow reading and you must have the outflow readings. So you need to monitor at these locations. And if I am looking at a landfill, just a few symbols. This is the landfill, partly above the ground, partly below the ground. I should monitor on the landfill surface. So these are just some sensors. Okay, and I would like to monitor here as well, and I would like to monitor here. If this is the inflow point, if the inflow drain is here, I would like to calculate the contaminants in the inflow water, and if this is the outflow point, discharge to drains, I would like to monitor here. I would also like to monitor here above. I may miss it. Something may go like this. So luckily for us, in gases and in liquids, mixing takes place as you go a little further. So you will hopefully be able to detect something at some location. Then I would like to monitor within the waste, because I can't get my contaminant of concern unless I am not taking out my leachate samples and seeing what is the contaminant that we want to do. It will depend on the type of waste. And I might want to monitor inside the gases. We are saying methane is coming out of municipal solid waste, but if I have hazardous waste, which are volatile organic compounds are we going to monitor for? So you monitor within the waste. Then you monitor immediately beneath the landfill. You want to detect early if there is any leakage. So you want to know if there is any leakage, I detect early, so I put a range of sensors, and I put some sensors in my three-phase media. That means you want to know how fast it is traveling. I've got something here, but there is no reading here, so maybe it has not reached the groundwater table. Then I want to monitor the groundwater. But as I said, if the groundwater is flowing in this direction, I want to monitor everything at the boundary. Inflow, outflow. So if I have a petrol station or if I have volatile organic compounds, maybe they won't reach the groundwater. You need to know whether the petrol fumes are going out. If I have total dissolved salts, I need to know what's going out. If I have heavy metal, I need to know what. So you need to monitor on the boundary. This is only the diagram on the section, an idealistic diagram. This is in plan. If this is my landfill, base of the landfill, then I would like to monitor at all these locations on the perimeter. If I have one inflow point for water and one outflow point for water, I should monitor that. Is there a single inflow point for air? No, ours is not a controlled chamber. I don't have a huge dome which is on my site. If I had a dome on my site, then I would say here is the inlet and here is the exhaust. So I will monitor where the exhaust is there. But I don't have that. So I need to monitor air all over the perimeter, and I need to monitor the groundwater all along my perimeter. But water I can monitor. And on the surface, within the waste, beneath the waste, you'll have several monitoring points. How we are going to monitor, we are not talking, but what we want to monitor. Looks very complicated, lots of points. But we need to optimize this. We need to be sure that we detect what is coming out. We don't need to put a large number of infinite instruments. Also remember the difference between monitoring and detection. Monitor is you have the facility, you have to keep a watch on it. The facility becomes the source. So the landfill is the source of contaminants, and I have to keep a regular watch on it. And our main purpose of monitoring is that contaminants in the emissions should be within the prescribed limits. That's one. And secondly, there should be no leakages, but if leakages do occur, we should be able to detect leakages early. In an old facility, suppose I have an old waste dump, it's not an engineered landfill. I have to monitor, but I can only monitor if I know the extent of the contamination which has already occurred. Because I'll find the extent of contamination and then I'll monitor where? At the boundaries of the contamination. Suppose I have a landfill and the plume has traveled. Suppose I have an old dump and the plume has traveled. Now I cannot start monitoring inside the plume. So as I said, if I have a new landfill which is well designed, I can monitor here and I can monitor here. But if I have an old dump where the contaminant plume, and says this is the water table, and the contaminant plume over 25 years is like this, my monitoring points have to be how does the plume expand or extend, or how does it become bigger. If I am going to monitor here, I am going to get the contamination. So in old facilities, find the extent of contamination and then monitor along the boundary. So remember, this may be your landfill boundary on the ground surface. But your plume may have crossed your boundary. So you will need to set up the monitoring points outside the boundary of your landfill. That's the difference between an old facility and a new facility. Detect. In detection, we do not know the source. So a report comes to you that the groundwater which is coming out of the tube well next to Himadri Hostel is showing high nitrates. You don't know the source. In monitoring, you know the source. In one case, you have got the containment, so you monitor within that. But in another case, it's an old polluting dump, you monitor beyond it. But if you are doing detection, it means one tube well will report to you some problem. Then you will go and start checking all the tube wells around or the hand pumps around that area. Ke bhi usme bhi problem hai ki nahi hai. Then you will say some tube wells are having a problem, others are not. Then you will say this is the boundary of contamination. Then you start checking the concentrations and then you will identify the source. Where is the contaminant coming from? Is it coming from a buried drum? Is it coming from a drain? Is it coming from somebody is injecting something at night because it doesn't have a treatment facility? So in detection, the source is unknown. Contamination is reported incidentally at a location. We have to identify the extent of contamination. That means do a site investigation to see how far this contamination is. And then on the basis of our results, we have to identify the most probable source. In industrial areas, there can be more than one source, but typically it's quite important to be able to identify the source. Sometimes the contaminant of concern will tell you the source, because you will like to know which industrial processes are using that source, that contaminant. Then you'll be able to identify it. In other cases, you'll have to make contours of concentration and then come and home in that this is where the concentration is the highest, and therefore it appears to be emanating from around this area. We are going to focus in this on monitoring. So as I said, these are the various locations in which you have to monitor: above the landfill, on the landfill surface, within the landfill, along the perimeter, beneath the landfill, at critical locations, at discharge points. What are the critical locations in a landfill? Especially if I am talking of subsurface contamination. What do you think is a critical location where leakage is likely to occur in a landfill? Where in a landfill will leachate always be present? Bottom, yes, everywhere in the bottom, but where? Which is the critical location? What is the sump? The leachate goes along the base of the landfill to a sump from where it is pumped out. So the sump always has leachate. It is not bone dry. It's like, trying to have a glass and you put a straw in it and say that I can pull out all the liquid with a straw. Can I? Now what do? Then you tilt your glass and you want to have the last drop of your very tasty aerated drink. You can, but you can't tilt a sump. So there will always be some leachate. So a sump which collects the leachate where the well is there and you pump it out is a critical location, right? It's like in your drain in the house, which point often leaks. It's not the pipe, it's the hodi or the drain sump where the water goes and collects and then goes, or the joints or the places where the water is being diverted. So a sump is a critical location. If you have an effluent treatment plant on site, that will become a critical location. Wherever you store leachate, suppose you are collecting leachate and you are storing it in a leachate holding tank. If the leachate holding tank is above the ground, then you can see the leakages. But if the leachate holding tank is below the ground, then it becomes a critical location. So you are going to do monitoring all over here, but this is both for all kinds of parameters. Above the landfill, you will monitor for gaseous emissions from the landfill, mainly methane in municipal solid waste landfills and volatile organics in hazardous waste landfills, but you'll also monitor the air. There are lots of issues about dust pollution. There's a lot of issue about fires and smoke, so air quality is important. That's above the landfill. On the landfill surface, again, you'll monitor methane emissions. You are interested in how much is the landfill settling, so you need to monitor settlements of the landfill. And this is important because landfills can settle by 10 to 15% of the height depending on the amount of organic content they have. And you also want to know about erosion. Are erosion gullies forming on the landfill surface? So you would like to monitor erosion. Within the landfill, there are two aspects which are of great interest to us, the leachate and the gas. So we want to know the leachate quality and we want to know the gas quality because that will tell us which is the contaminant of concern. So even before you go start sampling your groundwater, you go to your landfill, pick up your leachate, do a complete analysis of it for heavy metals, for organics, for inorganics, for dissolved salts, for chlorides, for sulfates, and say, okay, in this leachate, this is all above permissible limits. When it's going to mix with groundwater, when it is going to go through the Vado zone, it will be attenuated. But finally, these are the contaminants which are to be measured. So you find the critical contaminants. Those contaminants which are, those constituents which are within limits, they are not something you need to be bothered about. So within the landfill, check about the leachate. Within the landfill, catch the gas. You have the gas collection layer, you have the gas collection wells, take out the gas samples and analyze them. Also analyze the leachate head, means how much leachate is ponding up in the landfill. Sometimes your leachate collection and removal system may not function efficiently or it may become clogged. So you must know, is the leachate head building up in the landfill or not. Along the perimeter, as I said, you will monitor the gas or the air, you will monitor the surface runoff and you will monitor the groundwater quality. Beneath the landfill, I will be monitoring groundwater. Simplest to monitor is groundwater. It's easy to extract, you can monitor it. I'll be monitoring pore gas. What is the gas in the Vado zone, the partially saturated zone. And I'll also monitor the solid particles of the soil. At critical locations, I'll be monitoring at sumps, at leachate storage places, at effluent treatment plants, and at all discharge points. If I have a gas flaring unit, I'll be looking at the flaring unit. If I have chimneys or if I have gas wells which are doing passive venting, I'll monitor that at all pipe outlets. So this is where we have to monitor the various parameters. So the philosophy, now we are going to focus more on subsurface monitoring. The philosophy of Vado zone monitoring is different from the philosophy of saturated zone monitoring. Saturated zone monitoring, your first indicator that something is wrong is if the groundwater sample gives you something which is abnormally high in comparison to the background level. How do you monitor this Vado zone? How do you monitor the partially saturated soil zone? Can you take out groundwater from a partially saturated soil? It won't flow under gravity. If you want to force something to come out, you can apply some suction. Maybe some soil moisture will come out depending on how close it is to saturation. So Vado zone monitoring is good if you want to monitor pore gas. And this is done extensively around petrol stations, petrol tanks. But otherwise it's more cumbersome. So let's see. In the Vado zone, you can monitor the pore gas and you can also monitor the moisture. Is the soil becoming more saturated with time? is the soil becoming more saturated with time? That if it is, if the moisture content is going up, you know that something is leaking into the soil, right? You basically use suction samplers. Nothing is going to come out in a borehole under gravity flow. Moisture will be held under suction. Gas will also be held unless there is a gradient, and the gradient can only be established if you put some suction. You can put free drainage samplers, but they will only work if the soil becomes saturated. If a wetting front is traveling down, then you may get free drainage, but that is pretty late. And of course, you can put some geophysical probes. In the Vado zone, you can measure conductivity or resistivity, and if they change with time, one is a seasonal change because it's wet and dry and wet and dry. That's within the limits, but if something more happens, then you know this something is different. In the saturated zone, you will basically use wells or piezometers, groundwater wells, piezometers, basically standpipe piezometers, and then you will collect the groundwater samples using mini probes or suction samplers, going down the piezometers or going down the groundwater wells. We will also use something called multi-port wells, which I'll introduce to you in this class. I'm presuming you know what are groundwater wells, and therefore you have to differentiate between groundwater wells and multi-port wells. But here again the issue is you are only analyzing the liquid phase. If you want to do a very exhaustive analysis about your contamination, then you do what is called whole sampling. Then you don't try and suck out the moisture from a soil, you don't try and suck out the groundwater from a soil, you pick up the whole sample, whether it is saturated or unsaturated. This is called whole sample analysis. And what do? You bring it to the lab. Now if I've got a partially saturated sample in the lab, I'll bring it in a sampling tube duly sealed, and then from the sample I can take out the gas by suction, I can take out the moisture by suction, I can apply much more suction in the laboratory than I can apply in the field, right? So I can take out quite a large amount of moisture from the soil, and I can look at the solid matrix. So whole sample analysis requires you to get an undisturbed sample. And please differentiate between undisturbed sample for site investigations for foundation design. What is an undisturbed sample for foundation design? The mechanical properties should not have got modified. Means your strength should be the same as in the field, your compressibility should be the same, and your permeability should be the same. What is a whole sample for environmental concern? Not only should the all that was applicable for foundation design, but nothing should chemically change. You should not, while you're taking out the sample, the gas escapes. If you're taking out the sample, the water escapes. So you should be able to keep it whole. So whole sampling requires very careful sealing of the sample as soon as it comes out. Okay. So whole sampling down the borehole or using cone penetrometers. Very briefly, you can read up about pore liquid sampling in the Vado zone on something called lysimeters. We don't use lysimeters in soil mechanics so much, but a lot of agricultural engineers use lysimeters. And basically what is it? It's a kind of a tube with a ceramic or a porous cup, and you apply a suction in it, and you hope that the water will come into this tube, and then you can pull it out by suction. If it won't come out through suction, you can put some pressure in it and it will come out. The fundamental thing is you bury something into the ground which has got a porous tip. Porous tip, porous stone, ceramic tip, piezometers. That porous stone allows water and air to come in, but does not allow solids to come in. When you apply suction in it, if there is moisture, if the suction inside the lysimeter is higher than the suction being applied by the soil grains to the moisture will go into the ceramic cup or the porous stone, and then you extract it by suction or by pressurizing. So in the unsaturated zone, liquid is held by soil because of surface tension. Sampling is done by applying vacuum in samplers with porous tip. As you can see this, in situ negative pressure is measured, and suction is in the range of 0.6 to 0.8 bar. There is a limit to how much suction you can employ, otherwise it does not work, and these are the kind of devices you can use. if you are wanting to do free drain samplers, that means I only want to know when the liquid is coming out. I am not interested whether it is held. As long as it is held, it is not going down. So here, for example, is your clay barrier, and underneath that you can make a free drainage lysimeter, not under suction. You just put a gravel pack, put a filter between the clay and the gravel pack, and put a pipe, and it will be sloping and coming towards a sump at the side. The idea is that if this becomes saturated and water starts to drip down from here, it will get collected in the gravel. Between the clay and the gravel there has to be filter. Here it is showing a geotextile filter, but you can also have soil filter layers so that the fines don't travel into the gravel. So it's just a simple free drainage sampler beneath the clay. It's easier to sample gas in the vadose zone. So please remember, most of the time it's not the liquid that we are after. We are after the gaseous samples. So liquid VOCs can cause vapor concentrations in the soil pore space to increase. Landfill gas can also cause pore gas concentrations in the vapors to increase. Now luckily for us, we have a device called the gas chromatograph, which helps you analyze gas samples, and this is, luckily, these are also portable devices. You can actually carry a gas chromatograph in a handheld unit and take it to the field, and you can get online measurements of gas concentrations. So portable gas chromatographs are used for contamination detection. Sometimes these are called landfill gas analyzers. The word landfill gas analyzer is just a pseudonym. Basically they are a portable gas chromatograph. So you will, you can even walk with them. You can say, I want a methane analyzer. So the analyzer is designed for methane. You can walk over a landfill and get some readings. So gas surveying is done. You can do it only on the surface, or you can do it in boreholes up to the water table depth. And 3-4 devices can be used. You can make a borehole and you can send a probe in. You can make a borehole, you can apply suction, right? Or you can make a borehole and put a chamber on top in which there is an absorbent. So you say, is for this gas, this is a good absorbing material. So I will leave the chamber there for 1 week because I am not getting adequate concentration. But in 1 week that gas would rise and this absorbent will keep on absorbing. Right? And then you take that absorbent away and analyze it, that in 1 week how much of the gas I have absorbed in it. So you can have surface flux chambers, you can have suction probes, you can have down the hole probes, and you can have absorbents or surface accumulator devices. So typically it's nothing. If you have a tube, it's a metallic tube, conical tipped with holes in it, perforations in it. You can drill a borehole and put the tube in it. You need to seal it from the top because nothing should come in from the top. You can put a bentonite seal, and in this, if you apply suction in this space, just like in a tube well, in a groundwater well, water will come in, gas will come in and come out, and you can use the gas analyzer for determining the gas concentrations. I'll not talk about gas samplers, but there can be active samplers, passive samplers, and grab samplers. You basically need a sampling tube. This is a grab sampler. This is a bag which is collapsible. You will collapse it completely, and then you will inflate it by applying suction in this chamber outside, and here all the gas will be entrapped in it, and you can take it to your lab and then determine your concentrations. But let's come to our main business, which is groundwater monitoring and monitoring wells. So first is, how do we make monitoring wells? So I have made some lines here. So that's a well. That's a well. And what does it look like? It looks like it's basically a pipe which is sent into the ground, and if you send in a submersible pump, groundwater will come out of it, if there is groundwater which will flow into this pipe, right? So first let's look at the elements of this, and then we'll see how it's installed. So let's come back to this diagram. You make a borehole just like you make a borehole in your site investigation technique. So how do you make a borehole in your site investigation technique? Augering, percussion drilling, wash boring, jet, chiseling, anything else? Maybe many more. But you make a borehole. So suppose your groundwater is available at 20 meters below the ground surface, and you know that there is a pervious zone. So firstly you need to have a water bearing strata in which is pervious, where water will flow. So you make a borehole down to that level. After you have made the borehole, you will stabilize the borehole, and then you will put a pipe in it. What is the diameter of this pipe? 50 to 150 mm, 2 inches to 6 inches. In this pipe, there will be a screen. That means there will be a lot of holes or perforations in which the water can flow into this pipe, right? First you make the borehole. How do you keep the borehole open? In soil mechanics, how do you keep a borehole open? Most of the time we don't use a casing. Yeah, so don't give the answer in an inverted way. We can use a casing if you are going very deep, but if I am not going very deep, I will use bentonite. And if I am using wash boring, then the drilling fluid is bentonite slurry. It keeps the borehole open. So now you've got the borehole which is open, which is full of bentonite slurry. You're putting the pipe in it with screens in it, and then you put gravel all around it. Okay? What I'm calling a filter pack is typically a gravel pack. The idea is that when water flows from the soil, it will come into the gravel and then it will go into the screen. The fines will not come in. So you need a filter pack, or you need a material which is pervious enough for the water to come in but does not allow the fines to come in. And then in this pipe you can send a submersible pump and pump out the water. Normally you will seal. The screen will only be in the region where you want to take out the groundwater from. So here it says typically 50 to 150 millimeters dia, screen length, thickness of the pervious stratum, or typically 3 meters. So this may typically be 10 feet or 15 feet long, right? That means water will come from this region into this and you can pump it out. You will seal this. There is gravel at the bottom, but you will seal it with a cement or a cement bentonite grout so that nothing else falls from the top and contaminate this water. The water which you get out should only come from the soil, and there you can have the pump, and then you'll have a riser pipe and water will be taken away. So a well is basically a borehole with some annular material, the filter and a well assembly, and the drilling most often adopted is the rotary, mud rotary drilling or the wash boring. For environmental studies, hollow stem augering is preferred because remember, when you do drilling with drill fluids, you are actually putting into the soil some foreign material. Your bentonite slurry is coming from some other place, some other state, it's in a bag, you mix it with water and you put it into the ground. Then you say, I'm going to do environmental studies to check the groundwater contamination. First you please check the contamination of the bentonite slurry which you have put in and pumped in for 2 days before you were able to reach the full depth. What are you going to check if you are going to use a material which is imported, which itself may not be clean? The bentonite may have been made by a manufacturing process which would have put some chemicals in the bentonite itself. So therefore they say instead of using a wet drilling, always use a dry drilling when you are going to do environmental monitoring. And the dry drilling technique I have done with you, it's called the hollow stem auger. The hollow stem auger allows the borehole to remain open. It's a continuous flight auger, and inside the hollow stem auger you put your pipe, and as you withdraw your hollow stem auger you fill the gravel pack behind it. Typically we will need 4 wells. If this is the groundwater flow direction, let us say this is the groundwater flow direction, 1 well on the upstream side so that you know what is the quality of groundwater coming to the landfill, and 3 wells on the downstream side. Forget about this word well cluster at the moment. One well here and 3 wells here. Why? Maybe the groundwater plume will spread like that, you don't know. Maybe you have put a well here and inflow is fine, but the water goes like that, you will miss it. So typically you must put at least 3 wells around your landfill. So if I look at it in plan now, if that's my landfill or if that's the shape of my landfill and I know my groundwater flow is like that, which is not very precise, I will definitely put a well here, but I would like to put at least 3 wells here so that I can capture if there is any contamination which is taking place. What is the concept of well cluster? Why do you need a cluster of wells? The issue is that we don't know at what depth the contaminant will go. If I take a section here, let's say this is an above ground landfill, and let's say the water table is close to the ground surface, and I put my well here, right? Or if you want to look at this well, my well is here. Now when I make a well, my upstream well is here, I need to say where will my screen be. Why? Because then I will be collecting the groundwater from that area. So can you tell me where I should put my screen in this? Should I put the screen here or here or here? Maybe you will make a well in which the screen is here. You will say I will detect, because maybe the contaminant will float. You put it like this, but the contaminant is actually going like that. You will miss it. Your well will not get that contaminant unless your screen is in the way. So if you want to pick up samples from 3 depths, then you need to have, well, Mandeep will say, sir, क्यों इतना पैसा खर्च करते हो? स्क्रीन को बड़ा कर देते हैं. बिल्कुल ठीक है जी, स्क्रीन को बड़ा कर दो. I made a 20-meter long screen. How beautiful. I don't know from where the contamination is coming. Why? When I suck out the water is falling through the gravel pack. What's happening? When I take the sample, the water is falling through the gravel pack. This is coming as a mixed sample. So I'll say, okay, ji, from what depth is the contamination? Sir, it can be between 5 meters to 25 meters below because my well is collecting the sample from 20 meters. No, that is all right for drinking water. आपको क्या फर्क पड़ता है? पानी, water should be drinkable, and you have a thick 25-meter aquifer. It's not all right for environmental studies. So well cluster means you are trying to pick up 3 samples from 3 different depths which are isolated from each other. Water should not mix. So in this diagram which is shown to you, if I want to get water samples from 3 different depths, let me try and articulate this. One option is to put my wells in 3 separate boreholes. Please note, this is called a well cluster. I have 3 separate boreholes. These are my boreholes. Tell me where will be the gravel pack. In the first borehole, where will you put your seal and where will you put the gravel pack? In this borehole, water has to come from here. I'll put my seal here. Okay? And I'll put my gravel pack here. Agreed? When I draw out the sample, the water will come from this area. Where should my gravel pack be in this? Should I put my gravel pack from here? Put my seal here? Is this correct? My screen is here, water will come from here. No, this is not correct. When I start to pump out the water level inside will fall. Water will want to come in, it will come from here. Definitely it will come from here. But it will also come from here, and since there is gravel here, it will fall down and mix with it. So your seal should be, all this should be sealed. If you want the water to come from this zone, there should be a seal above that zone, that when you take out the water sample, water is only coming horizontally from that zone. So 3 different wells to give you 3 samples from 3 depths. इसमें आपकी seal यहाँ तक होगी. So the question is, can we put the 3 seals in the same hole? Let me try and do this. Why should I have to make, drilling 3 wells is much more expensive than drilling 1 well. Can I put the 3 seals in 1 hole? Let me make the full. Let me send the pipe. Let me seal this. यहाँ ग्रेवल है, यहाँ ग्रेवल. Let us say the water table is here. What will be the water level inside the well? Now I have got 3 locations. When I suck, the water will come from here, the water will come from here, and the water will come from here. It won't mix from these areas. Agreed? So I've got 3 locations. इस well में पानी कहाँ होगा if I'm not doing any pumping? If I have any well, what will be the level of the water inside the well at any point of time, whether it's an open dug well or a tube well? Groundwater table. So without pumping, the water level will be here. Now you come today and say, I want to take the sample. I want to take the sample from this depth. What happens? You send in a pipe and suck out the water. But once you start sucking out the water, this water will also rise. The column is mixing the water. You have now separated the 3. Water won't come from this layer. Water will always come from this layer, and water to this will come from this layer. But inside the pipe it's getting mixed, because जब आप इसमें पाइप डालोगे पानी नीचे हो जाएगा, फिर पानी अंदर आएगा और नीचे वाला पानी भी मिक्स हो जाएगा. So the water column itself is not isolating the water. Whereas here, it's only the water coming through this soil that you are able to pick up. See, here also the water table will be here. Agreed? But the water in this column has come from where? It has only come from here. No water has come into this column from this side. When you pump this, water level will fall. More water will come from here. So now if you read this, we have to use well clusters for multi-level sampling. I am using a 3 well cluster with 3 different depths. Well material, so firstly you do not use steel pipe. Most of the time we have been using steel pipes now. We have gone to PVC casings which are perforated with screens. Well materials should not contribute to contamination. That is the filter pack, the drill fluids, the seal materials, the grouts and the lubricants. Each one of them has to be tested that they do not cause contamination into the ground. We have to develop the well by removing drill fluids. Suppose I have used some fluids. I have to keep on pumping out the well for a few weeks, which is called well development. So what will happen? Then whatever I have injected into it is taken out. Then the well is ready for sampling. So we have to do well development. And I have to do sampling using balers or pneumatic samplers, PVC samplers. And please remember, please remove 3 to 5 casing volumes before each sampling. You are going to come to this well and say sample every week. So the well will have water to the top. Before you take a sample, you have to remove 3 times that water, 3 to 5, because that water which has been stagnating in that well inside that tube is not the representative water. You take it out once, it will fill up again. You take it up again, it will fill up again. 3 times you purge it. Then the sample which has come inside is now representative of the sample which is coming from this location or this location. So purging has to be done by removal of 3 to 5 casing volumes before each sampling. So that is the way in which we extract the samples. But there are devices which are called multi-port devices. In one well, these are highly sophisticated devices. In one well, we are able to take out samples from different locations. These are called multi-port wells. But in this, there is a difference. I do not pump out. I send a sampler to each level. This port can be closed and opened remotely. We send the sampler to each level and extract the sample from that port. And we will do this in the next class as to how to take samples in a single well using multi-port devices. The problem is this is a very sophisticated well. It takes a lot of expertise to install it. Once you install it, it works very well. But I'll come back to this. So far, we were talking of sampling by suction, pump dala. But I used the word sampling by a PVC baler. So what I would like to do is, suppose I want to take a sample inside a river, a water sample inside a river at different depths. How do I take out a water sample in a river from different depths? How would you do it? One very normal photograph you see is person putting a bottle into the river and taking out a sample, or you'll go in a boat and you'll put a bottle. Sometimes it will be attached to a long rod and you'll take. But that's all superficial sampling. I tell you that we are going to take a sample in the river Yamuna from 12-meter depths. Can you tell me how you'll do it? I'll put a pipe to 12-meter depth and I will suck out everything from the pipe, and a lot of water will come into the pipe as you suck out. So that water into the pipe will also not be from 12-meter depth. The first will be from 12 and the other will be from all around it. There is no screen in it now, we are in water. So let's say we send a pipe and the bottom of the pipe is at 12-meter depth. How are you going to take out the water from that 12-meter depth and not from 13-meter depth and not from 11-meter depth in your sample? I'm doing a sampling with every half a meter. How am I going to do it? So you need to send in a sampler which opens at that depth, has vacuum inside it, and samples it and closes, and when you bring it up, it doesn't mix with anything on the way. So when it goes down, it is not open. So let me take a sampling bottle in which there is air pressure with the ball valve, and because of the air pressure, the ball valve keeps the bottle closed. You reach 12-meter depth, you release the air pressure. What will happen? The ball will fall inside, water will come in from that area only. Then you pressurize again and the valve will close. Now you bring up the sample. So that is a mechanistic issue. The issue is you need a sampling device which goes to a depth, picks up the sample from that depth, and as it goes down and as it comes up, it doesn't allow any liquid to come inside it. So that is what we are talking of, using PVC samplers which open at specific depths, and these are what are used in these multi-port devices. But even in these wells, instead of trying to suck out, you do 3 to 5 casing volumes of purging, but next you can send in your sampler, which is like sampling in a river, send it down and pick up the sample only from the depth where the screen is. Don't try and pump out the whole water all the time. So we can have different samplers, pneumatic samplers and PVC samplers, where you can actually get the sample from a particular depth, and we'll look at this in the next class. So we'll stop here today, and all that I have introduced to you is how do you make a well, and how do you take a sample out of a well, and how a well will not give you a sample from a particular depth, it will give you a sample which represents the entire zone in which the filter pack is there. Your screen may be at the bottom, but if the filter pack is there, typically in all wells where we are trying to get out drinking water, there will be a huge filter pack all around it. Why? You want to maximize the amount of water which can come into the well. So there is not an attempt to find what is the groundwater quality at a particular depth. So you have to make these special monitoring wells where you can get the groundwater samples from that specific depth. So in the next class we'll look at multi-port wells, and we'll look at other devices through which we can monitor the subsurface environment. So any questions? Okay, then we'll stop here.